welcome to this channel Chemistry Made Easy by Dr.ARM. Today we will see the next part of the polar molecules which we have studied or discussed last time. Now we will see some examples here, and we have seen the introductory part, that is what is meant by dielectric constant, bond polarity, molecular polarities, and the magnetic moments. Now we will see here some examples related to this point. So these parties of polarity of molecules, and we will see the examples. So first example is of NH3. So this is ammonia molecule and its structure is like this. It has one lone pair and 3 bond pairs. So compared to these nitrogen and hydrogen, the electronegativity shows that nitrogen is more electronegative than hydrogen. So the dipole moment is pointed in this direction. Then this lone pair is away, pointing away in this direction. So the molecule shows that the polarity of the bonds is directed in this direction, as well as the polarity of this lone pair is also directed in the same direction. So this reinforcing property shows that there is large increase in the bond polarity and total molecular polarity. So we can show this in this way. So the dipole of the molecule is pointing in this direction, and the dipole of these bond pairs is pointing in this direction. Dipole of this lone pair is pointing in this direction, and total molecular dipole is pointing in this direction. Now because of this, it has this terminal has delta positive and this has delta negative charge. So this shows that the net dipole of this molecule is 1.47 D, and this calculated dipole is 1.85 D. So the calculated dipole and net dipole has some difference, but this value shows that the dipole of the moment molecule is very large. So this is because the dipoles of the bonds pairs and non-bonding pair is pointing in the same direction. Now we will see next molecule, that is water. Second molecule, water. So it has structure like this. It has 2 lone pairs like this. These are bond pairs. The direction of the dipole in this molecule is like this. and the lone pairs are pointing their dipole in this direction. So the net dipole of this molecule is pointing in this way. So it has delta positive terminal, this has delta negative terminal. So you will find that here the net dipole is 1.85. Net dipole is 1.85 D, whereas calculated dipole is 1.86 D. So this is higher value of the dipole moment of the molecule. This is because why there is such large increase as compared to that in NH3. This is because the bond pairs are also pointing in the same direction. That is, the dipole of these two bond pairs is pointing in the same direction, as well as the dipole of the two lone pairs is also pointing in the same direction. So the two dipoles are reinforcing each other, and the resultant dipole of the molecule is becomes very large. Then we will see third molecule. That is NF3. So here nitrogen is at the center, and these are the nitrogen fluorine bonds, and lone pair is in this way. So this will show that if we compare this nitrogen fluorine, fluorine is more electronegative than nitrogen. So the bond dipole is pointing in this way, in this direction. And the electron lone pair, the lone pair electron shows that the dipole of this lone pair is pointing in this direction. So it is, if we see the net effect, then it shows that the bond molecular dipole is pointing in this way. This is slightly electron deficient, and this is electron rich, that is delta minus. So you will find here that the lone pair dipole is in one direction and the bond pair dipoles are opposite to it. So this opposing effect reduces the net dipole of the molecule, and it shows that the net dipole is very less 0.23 D. Similarly, if we find the calculated dipole, it is 0.32 D. So compared to H2 and NH3, you will find that the dipole moment of this molecule is much less. Why it is so? This is because the bond dipoles and lone pair dipoles are acting in opposite to each other. As a result of this, the dipole moment of the molecule is reduced. Then we will see other examples. The first is CH4. So it will have structure like this. So in this molecule, you will find that compared to hydrogen, this carbon is more electronegative. So the bond pairs are having dipoles in pointing towards the carbon. So this electron density is moving in the same direction, means towards the carbon. So as a result of this, the electron density is distributed equally. So such molecule has zero dipole. Dipole is 0. Similarly, we can have another molecule, that is CCl4. CCl4. So here you will find that compared to carbon, chlorine is more electronegative. So the bond dipoles are pointing towards chlorines. So the electron densities are moving the way. So the dipole moment of this is also 0. Because bond dipoles are moving in all opposite from each other. Means there is no any particular direction in which the dipole moment is concentrated. Then we will see third molecule, that is SO3. That is SO3. So here also you will find that the dipole moments of the bond pairs is equally distributed. Means distributed all over the molecule in the equal directions, or simply all around the molecule at equal concentration. So dipole moment of this molecule is also 0. So all these molecules have symmetric structure. So all these molecules have symmetric structure, and therefore their dipole moments are 0. So the individual dipoles of these bonds are cancelling each other. So if we see such non-polar molecules, so such non-polar molecules have attractive forces in equal, means about all over the molecule in different directions, and therefore there is no net dipole moment of the molecule. Even though such molecules are showing 0 dipole moment or relatively less dipole moment, because the carbon atom and hydrogen atoms have difference in their electronegativities. Here carbon and chlorines are also having difference. So such molecules are having little dipole moment, but the net dipole moment of the molecule becomes 0. But when there are sometimes fluctuations in electron densities in the compound or molecule, there is development of temporary dipole moment in the molecule, but it rests or it is existing for a short time, very short time. And even though such temporary development of this net dipole moment, it causes the change when one molecule comes in contact with other molecules. So temporarily developed dipole moment attracts the electrons of neighboring molecules, and there is development of some attractive force. So it causes the net effect or overall effect resulting in the attraction of all molecules. That is, this negative terminal will attract the positive terminal of other molecules, relatively less electronegative terminal of other molecules. Means electron densities of remaining molecules are showing influence on the dipole moment of this molecule. So this will develop the net dipole, and because of the fluctuation in electron density in the molecule, there is development of attractive forces, and these attractive forces are called London forces. London forces or dispersion forces. London forces or dispersion forces. So such forces are responsible for liquefaction of the compounds which are present in the gaseous state, like hydrogen, oxygen, carbon dioxide or nitrogen. So the liquefaction of such molecules, hydrogen, oxygen, nitrogen and carbon dioxide, is possible because of such temporarily developed forces, that is London forces. And this will have again very disturbances, because when the two molecules, say for example two molecules of two hydrogens are coming together, then the two nuclei are separated by electrons present around it. So the electrons between them, that is bond pairs, are shielding the nuclear charge, nuclear effect of nuclear force of attraction. So this shielding of the nuclei by inner electrons is showing some magnitude of polarization. So the electron cloud is more polarized in such molecules. So with this we will stop here, and in the next lecture we will see the next point, that is hydrogen bonding. So till then, goodbye, see you next time. Keep watching this video and sharing it, and please press bell icon and like button. So thank you very much.